Hey everybody, it's been a long while. I haven't done a video in a long time on this channel. I'm trying to do a study video here for the electrician's apprenticeship. A little late to this subject, so I'm gonna start doing book 1, session 13 and 14. Book 1, session 13 and 14. This is dealing with mostly DC theory, cold standard practice, and conduit fabrication. We're gonna be dealing with, in the DC theory, we're gonna be dealing with voltage, current dividers, voltage across parallel circuits, and how to calculate power on parallel circuits and resistance on parallel circuits. Okay, and then we're gonna go into some other things as well with the conduit bending, the push through bending 90 degrees bend, bending kicks, offset, saddles using push through method, because it's gonna have a lot of terminology in that involved in that too. So this, as if I haven't informed you yet, this program is mostly for to help memorize a lot of information, and it's meant to be verbal. Like a verbal study guide, so that people can play it while they're at work or something, and help study while they're at work. Just listen to the stuff here. So first of all, to get started here, there's a few formulas I wanted to kind of run through here for memorization. So sometimes I will repeat stuff a couple of times because I'm trying to help people memorize stuff through audio methods. But I'm gonna point to some of the stuff in the book too, sometime here and there. Okay, so when it comes to this parallel circuits, one of the formulas we can use to merge, to merge the two resistors in parallel together, is the product over sum method. So that will be the R total equals resistor 1 times resistor 2, all of that divided by the resistor 1 plus resistor 2. So it'll be think of it as a fraction. The resistors total equals resistor 1 plus times resistor 2 over resistor 1 plus resistor 2. So resistor 1 times resistor 2 over resistor 1 plus resistor 2. So at the top you got multiplication, at the bottom you got addition. We call it the product over sum method. And that way you can merge two resistors together to get one resistor to merge into one resisted factor. But that won't give you the total resistor of the whole circuit. That just gives you those two resistors put together. It merges those two together if they're in parallel. Whereas you have the other method, the reciprocal method, which you have resistor total is 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3, etc., etc., etc. So you add up all. So you take the reciprocal, which is 1 over whatever the resistors are, and you add, and you do that for each resistor, adding each one of them together. So 1 over resistor 1 plus 1 over resistor 2 plus 1, etc., etc. And whatever value you get for that, you place 1 over top of that. So it'll be 1 over whatever that sum is. That will be the value of resistance total in the parallel circuit. So remember those formulas there. Okay, now sometimes you got resistors with the same value. That will be the resistance total equals R divided by the number of resistors. So if you got, let's say you got 330 resistors in a parallel, right? Well, it's going to be the inverse. It's going to be the inverse proportion, I believe, and it's going to be, each resistor is going to be 1/3. See what I'm saying? Because you got the resistor, what I say, 30, and you're gonna divide it by 1/3 by 3, which will give you 10, right? And I believe the resistors in parallel are going to be this the total resistance is going to be less than any individual resistor, from what I understand. Okay, let's continue on. Okay, hold up here. Work with me here. Okay. We know in a series circuit, the I stays the same, right? In a series circuit, right? Whereas in parallel circuit, the I is added up. So I1, I plus I2 plus I3, etc. is the I total. Where voltage in the parallel stays the same, where voltage is additive in the series method. I mean, in a series circuit, excuse me. And that brings me to another formula that we need to remember, which comes power. So we have power, right, equals I squared over R. Remember that formula. Power equals I squared over R. Let me correct myself there. Quote myself there. P equals I squared times R. So power is current squared times R. Current squared times R. Now here's where the formula changes here. So when you don't have the current, you can use voltage here. Voltage squared divided by R. So the current total, the total current squared times the resistance total will give you the power total. So when you got I, you multiply times R. Will give you P, but you have to square I. So I squared times R. Whereas E squared divided by R will give you P. So E squared, the total E squared divided by R total, or resistor total, will give you the power total. Make sense? So P equals I squared times R, or P equals E squared divided by R. It's kind of similar to the circle when you think about it. Let me see if I can pull that up. Ohm's law wheel. See, here's the Ohm's law wheel, where you got P, where we got I, remember I squared times R, and see how similar that is right down here to I times R is E. See how similar that is to there? It's squared now. And on the flip side over here, where is that? E squared divided by R give you P, right? Right? And then you got, for R, E squared divided by P right here. So E squared divided by R give you P. But for I, you got E divided by R over here. So it's all, you memorize these formulas. Not to confuse you, memorize these formulas. It'd be very simple. Very simple for understanding a lot of this stuff. So I squared times R is P, and then E squared divided by R is P. Remember that. So let's get back to this thing here. Okay. So the voltage stays the same in the parallel circuit. So we'll use that Ohm's law formula to find, like, the current. Say we want current for the resistor 2, right? We have the voltage divided by R2, or resistor 2, will give us the current 2. See that? And remember, all the currents added up, from one side has to be the same thing on the other side coming back. Remember that. So if the current has coming in, got 4 amps on total coming in, it's going to be 4 amps returning as well. See what I'm saying? So remember that. Each resistor has its own current path. Okay. Let's see some more stuff here. So like I said, I total, or current total, will be you just adding all the currents up, and we'll be on one side, be on the other side returning. Let's see some more information here. Okay, let's see. Okay, series resistors in series versus parallel. Series, in a series circuit, the total resistance is the sum of all individual resistance in the circuit. As I said, resistor total is resistor 1 plus resistor 2 plus resistor 3. That's in a series circuit. But whereas in parallel, here we go. In parallel circuit, the overall resistance is smaller than any of the individual resistances. The reason for this is that each new branch resistor draws more current from the source to increase the total current. Okay, that makes a lot of sense, since with parallel circuits, they don't use all the same current. See that? They don't use the same current. They have the same voltage, but they don't use the same current. So that's why the resistors have to adjust. See that? Okay, let's see. And as I was saying, resistance with the same value is the resistance. The resistance total equals resistance of any resistor. This is when they all got the same value. So if you got 30, 30, 30, it'd be 30 be the resistance of any value divided by the number of resistors. So if we got 3 sets of 30, then that'd be 30 divided by 3. Should we say it was 10, right? Okay, we went over this product of some method. It says when two unequal resistance in a parallel, when there are two resistance in parallel, when there's two resistors in parallel, but their values are not the same, the total resistance can be found using a formula known as the product over sum. The product is multiplying them over the addition, sum of its addition of them. So like R1 times R2 over R1 plus R2. It will give you the resistor total. That's how you can, put the two together. You can use that for more complicated problems. I saw some examples of that in the book. I'm going to see if I can get to. And see, we got here 3 or more unequal resistors in parallel. That's when you use that reciprocal method, where you have 1 over R1 plus 1 over R2 plus 1 over R3. You can use this method to add up the different resistors to get the resistor total as well. And you can also, by the way, this product over sum method here, with R1 times R2 over R1 plus R2. Let's say you have 4 resistors in a parallel. You can merge. You can, in a 3-step process, you can use this formula to merge the each of them together in sets of 2, like 2 by 2, and merge these 2, and then merge the final 2 together. You get, in 3 steps, you get the parallel, the total resistance of those resistors in that circuit. You can use that method to merge them. You can use that. for what I was told. Okay, let's see some other stuff here. Put the phone down a little bit. Let's see. More information here. Okay, so we know in parallel how they work. You know, where if like in series circuit, one of them burns out, we know, then the whole circuit is incomplete now. So it will shut off. Whereas in parallel, if one of the lamps were to burn out, it still will complete its circuit because you have multiple paths for it to return. Okay, it says voltage drop across parallel loads. When loads are connected in parallel, voltage is dropped across each load as in a series circuit. However, the entire source voltage is dropped across each resistor. The reason for this is that all parallel loads are connected directly across the power source. I'll say that again. Voltage drop across parallel loads. When loads are connected in parallel, voltage is dropped across each load as a series circuit. However, the entire source voltage is dropped across each resistor. The reason for this is that all parallel loads are connected directly across the power source. Whereas again, the voltage is the same in the parallels. It stays the same. So ER1 is equal to ER2 or is equal to ER3. It says connecting batteries or cells in parallel has the effect of increasing the area of the plates. When connecting in parallel, the voltage remains the same, but the amp hour capacity increases. All sources must be the same voltage when connected in parallel. So this is connected voltage and sources in parallel. So when you're adding, we have the when you connect the batteries or cells in parallel, it increases the area of the plates. And let me see, it increases like when they're in parallel, it increases the capacity. Think of it like the capacity of it. It increases the capacity of it, but it's still going to dish out the same amperage. I mean the same voltage. Excuse me, the same voltage. When batteries are connected in parallel, their voltage remain the same and their amp hour capacity are added. Okay. And this is going back to some of the formulas that we was talking about earlier. Power in series versus parallel. Where we got P equals P equals E times I. And in parallel, that same concept is used. P total equals E total times I total. Same concept. Like I say, it's the same concept for that we went over earlier. But here's the thing. The total power is the sum. This is in series. The total power is the sum of the power consumed by each resistor. That's the total power, watts, right? You add the power from each resistor. The total in parallel, the total power is equal to the sum of the power consumed by each branch of the parallel. And we're going back to our little wheel. You know, I always use the formula. You know, V equals, or E is in this case they call it E. E equals IR. E equals I times R, and then I use the mathematics to kind of reshape that equation to get what I need. And we was talking about earlier, I squared times R is P, right? But E squared divided by R is also P. So just keep that in mind. Those are some of the equations you gotta memorize too. But you can also solve for those as well if you do forget them. Okay. Now let's see some other stuff here that I got here. See that this packet is closed here. So let's go over some of these questions on these let's go on some of the online questions. Let me find some of them. Okay. So we can start memorizing. That's this one here. Let's see, let me get to the chapter in the book. Be patient with me, please. Be patient with me, please, and I'll get to the information in the book. Okay, here's some definitions, some glossary definitions too, in this chapter 5 of the DC Theory book. This is what it looked like, DC Theory. See, chapter 5. Some glossary terms. It says assumed voltage method. Right there. In a parallel circuit, the total resistance can be calculated by using an assumed voltage with known resistive branches. This assumed voltage produces values of current but will calculate actual resistance. This formula is E total assumed over I total assumed equals resistance total actual. Right? Okay. We went over this product over sum method. We went over this. Okay, we went over some of this stuff already. Let's see here. I'm trying to see anything else before I go to the information in the book. We went over the reciprocal method. Okay, looks like I went over a lot of stuff here. Okay, so let's go to the stuff on the test. So your homework. Let's see. Hold up with me. Let's see. Let me pull some stuff up. Okay, here's a question. It says, in a parallel circuit, with a single power source, the current that leaves and re-enters the power source is called the total current. That should be simple. In a parallel circuit, with a single power source, the current that leaves and re-enters the power source is called the total current. I told you on one side, what comes in leaves out the same, leaves out on the other side. Okay, let's go to the next question. Branch current in parallel circuits are always greater than the total current. True or false? That's false. Branch current in parallel circuits are always less than the total current. Got that? So repeat the question. Branch current in a parallel circuit are always greater than the total current. That's false, because the branch current in a parallel circuit is always less than the total current. Remember, it adds up. So, and speaking of, so right here, what formula for finding the total current in a parallel circuit when branch circuits are known? Again, I1 plus I2 plus I3, etc., 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 because remember, it's added up in parallel. Whereas it stayed the same in current. I mean, in a series circuit. So when you have a combination of the two, you know when you have the series circuit versus when you have the parallel circuit. Remember, this is added up, so don't get confused by that. Next question. Okay, it says adding parallel loads to a circuit will increase the total circuit resistance and increase the total circuit current. True or false? That's false. Adding parallel loads to a circuit will decrease the total circuit resistance and increase the total circuit current. Got that? So the question again, adding parallel loads to a circuit will increase the total circuit's resistance and increase the total circuit's current. That's false, because adding parallel loads to a circuit will decrease the total circuit resistance and increase the total circuit current. Because remember, the current is added, so this obviously that's going to increase. But remember, with the resistance, is different in parallel, because the total resistance goes down, and remember, it's less than any individual resistance, as we saw earlier in the book. It says, what formula is used to find the total current in a parallel circuit when the total resistance and applied voltage of the circuit are known? Okay, what formula is used to find the total current in a parallel circuit when the total resistance and applied voltage of that circuit are known? You use I total equals E total over R total. Remember the same circle mathematics, because I times R equals E, so E divided by R will give you T. We'll give you I, excuse me. We'll give you I. I apologize. Okay, let's go to some more. Okay, what fraction of a total current that is supplied to the load will be provided by each of the 4 equal rated batteries connected in parallel to the load? Okay, the answer to that is 1/4. So it says, what fraction of the total current that is supplied to the load would be provided by each of the 4 equal rated batteries connected in a parallel to the load? It says 1/4. So you divide up each of them by the numbers. They all got the same. It says they got the same resistors. So you got 1/4 is the answer there. I think it's called the inverse. What was that? Let's see if I can find it in the book. What it's actually called. Then I give you the definition. Let's continue. Okay, this was a mathematical problem. Okay, it says if a circuit has 3 branches with a branch's current of 10 amps, 5 amps, 12.5 amps, what will be the total circuit current? And it says we're going to find the answer to 1 decimal place. So in this case here, what will happen here is that you will have to add each of these up. We'll give you this 27.5. So we got 10 amps, 5 amps, and 12.5, because you got, remember, you just adding them up on the current. See, here's the thing, current here. So these are all current with amps, and you want the total, so you got to add them all up. See, I1 plus I2 plus I3. Bam. Okay, a break in any branch of parallel circuit will cause a decrease in the total current of the circuit. That says true. This answer is true. So a break in any branch of the parallel circuit will cause a decrease in the total current of the circuit, because it's added up together. Remember, it's added up. So If you take off one of them from something that's adding up, you're gonna get less. When you think about it, right? So, true. If two 6-volt sources are connected in parallel to supply a 24 ohm load, how much current will flow in the circuit? Okay. So let's see here. It says 0.25 amps. So we got two 6-volt sources connected in parallel. So that means that the capacity is gonna increase, but the voltage is gonna stay the same. And then you got a 24 ohm load. Okay, so the resistance is 24 ohms. Okay, and we're trying to find the current. So we got 6 divided by 24. Yeah, would give you this 0.25 amps. So yes, E. Remember the mathematics of it. E equals IR. So I gotta rewrite that formula off for I. So I equals E divided by R. And E here is gonna be 6 because remember the voltage stay the same when they connect in parallel with another battery. It stays the same. 6 divided by the resistance, which is 24, which should give us 0.25 amps. Will I explain that? Well, okay. If two 6-volt sources are connected in parallel to supply 24 ohms load and the current is 0.25 amps, how much current would each source supply to the load? Okay, so how much current would each source supply to the load? Okay, you got 0.125. Okay, here we go. We got another formula. This is IS equals I total over NS. So we got two battery sources, I believe, with a current of 0.25. So so we got IS equals IT over NS. So remember that. IS equals IT over NS. So the total current 0.25 over the number of sources of current, which is 2. We had 2 batteries. It gave us this number here, 0.125 amps from each. Okay. Okay, next. Let's see. Find the total current in the circuit by calculating the individual branches current and then use the sum rule for a total parallel circuit current to determine the total. Okay, so let's see what we got here. So we got 98 volts, and you could do that. Remember, we could do that product over sum method to merge these two together to get the total resistance. Remember I was telling you about that? The product over sum method. Let's see what they did here. They took the resistors. They got the current for R1. They got the current for R2. And then just added them up to get the total current. But yeah, I mean, yes, that's right actually. But you could have got the total resistance here and had the total resistance divided into this 98 here, and would have got the also got the answer that way too. But in the future, again, you can use the product over sum to merge these two together, so you have one resistant value. Because sometimes these can get really complicated. Let me see if I can get to that in another chapter in the book, in this recording. But let's continue. What's the total resistance of the circuit? Again, the product over sum method. But what they did was RT equals ET over IT. So we had from the last equation, we had the IT, which was 4.9, and they just divided that into E total, and they get R. Or again, like you do the product over sum method. So let's, we could try it here. Let's see. Let's try it. Because the answer is 20. So let's say 70 times 28 equal 1960. Okay, remember that, 1960. So 70 plus 28. Okay, you got 98. Okay, 60 divided by 28. I'll give you resistance total. Wait, I must have did something wrong. Hold on, I did something wrong. I did something wrong. What does it do? Hold up, I did something wrong. See, that's what I'm saying. Sometimes you have to check your work. I did something wrong here. Okay, so we got 70 times, what did I do? Did I do 70 times 28? I think I did. 70 times 28 equals 1960. Okay, and then we got 70 plus 28. 98. That's it. 1960